hydrogen peroxide H2O2, hydrogen peroxide. It is a very important laboratory reagent. We will learn that, of course, in the properties. Preparation. Any peroxide plus dilute acid, you get hydrogen peroxide. Any peroxide, you should start with a peroxide. Look here. Na2O2 plus H2SO4 dilute. Will you get H2O2? Depends on whether this is a peroxide or not. Is Na2O2 a peroxide? We discussed it in the oxidation states part, the last lecture. Na2O2 plus 1 plus 2 minus 2, O2 2 minus. So, when O2 2 minus, if O2 is 2 minus, we know it is called a peroxide, or O minus, or oxygen single bond. There is a lot of chemistry in this oxygen single bond, you will be surprised. Too much of chemistry is there in oxygen single bond, compounds containing that peroxy bond. Now, Na2O2, so therefore this is a peroxide, sodium peroxide plus H2SO4, you will get Na2SO4 plus H2O2. This is called the Merckx process, names not necessary. H2O2. PbO2 plus H2SO4. Will you get H2O2? Will you get H2O2? You will if this is a peroxide. If this is a peroxide, you will get H2O2. But is PbO2 a peroxide? Let us see. Give minus 2 to oxygen, minus 4. Lead is plus 4. Therefore, it is not a peroxide. Oxygen is minus 2 here because lead does not mind giving minus 2 to oxygen. Lead does not mind allowing oxygen to be minus 2. So, even if it is minus 2, lead can still take plus 2. Therefore, not a peroxide, not a true peroxide. Why do you say it is not a true peroxide? Earlier it was called lead peroxide. Though it is not a peroxide, it was called peroxide. Therefore, you don't get H2O2. Next, BaO2 plus H2SO4 dilute, you definitely, this is barium peroxide, plus 2 minus 2. Barium is fixed, you know, barium has a fixed oxidation state, plus 2 only. Barium can be plus 2 only, therefore this is minus 2. You will get H2O2. But along with H2O2, you get BaSO4. And this BaSO4 precipitate forms a layer on this BaO2. Therefore, this method is not used. This method is not used because BaSO4 forms a layer. So, that is the role of BaSO4. Wherever you have BaSO4, that does not allow the reaction to go further. It almost acts like a negative catalyst. So, you find BaSO4 at many places where the reaction does not go to completion. It stops midway through. So, BaSO4 forms a layer. Therefore, this is not used. Though you get H2O2, this is not used. So, then how is H2O2 prepared from barium peroxide? BaO2 plus H2O plus CO2, you get BaCO3 plus H2O2, H2O2 hydrogen peroxide, H2O2. So, how is hydrogen peroxide prepared in the laboratory? By adding dilute acid to this one. Next, it can also be prepared by the electrolysis of electrolysis of 50% H2SO4. Electrolysis depends on the concentration of the electrolyte. Suppose if you take concentrated H2SO4, what do you mean by concentrated H2SO4? It doesn't contain much of water. No water, no ions, no electrolysis. Concentrated H2SO4 means ionization will not be there. And dilute H2SO4 means it is nothing but water. Dilute H2SO4 is nothing but water. The water, some is added. So 50% H2SO4, it will undergo partial ionization. It produces H plus and HSO4 minus ions. H plus and HSO4 minus ions. And H plus ions are liberated at cathode. You get H2 at cathode. And this HSO4 minus goes to anode. And it will become H2S2O8, which is called per-disulfuric acid. Per-disulfuric acid, also called Marshall's acid. Names not necessary. And when you add water to this H2O, you get H2SO5 and H2SO4. This time it is called per-monosulfuric acid. Per-monosulfuric acid, also called Carros acid. Carros acid. And when you add more water to this H2O, you will get H2O2 plus H2SO4 again. Okay. So, electrolysis of 50% H2SO4, H plus HSO4 minus will produce H2S2O8 and H2SO5. Industrial method of manufacture of H2O2. Industrially, H2O2 is manufactured like this. Industrial method. This is called anthraquinone. 3 benzene rings, fused benzene rings, it is called anthracene, and double bond with double bond, this is called anthraquinone. This is 2-ethyl anthraquinone. You start the numbering here, 1, 2. 2-ethyl anthraquinone. Anthraquinone. 2-ethyl anthraquinone ketone. You just heat that with H2, hydrogen. Of course, in presence of palladium, H2. What will happen? You will get 2 OH here. Ethyl anthraquinol alcohol. Anthraquinone is converted to anthraquinol. Means just hydrogens are held by this molecule. This molecule has held hydrogens in its hand. Then I heat that with oxygen of air. And you get this H2 and O2. Once again you get H2O2. These 2 hydrogens and O2 means initially that substance must have absorbed that hydrogen, and when oxygen is given, it is giving back, and you are getting your 2-ethyl anthraquinone once again. You get your original product, 2-ethyl anthraquinone you will get. You can. So what are you actually spending? Hydrogen and oxygen. So you are in a way combining hydrogen and oxygen to give H2O2. This is the industrial manufacture. And you get your 2-ethyl anthraquinone back. 2-ethyl anthraquinone once again you will get, and you can use that again, recycle. That is about preparation of hydrogen peroxide. Hydrogen peroxide has got a special property. Concentration of H2O2. I am not talking about measurement of concentration. Here concentration of H2O2 means dilute H2O2 to concentrated H2O2. Suppose there is a lot of water, dilute H2O2 to concentrated H2O2. Concentrating a solution of hydrogen peroxide, a dilute. Usually what can we do? By heating, what will happen? Water will evaporate. You will get concentrated H2SO4. Something like distillation. Because the boiling point of H2O is 100 degrees centigrade and the boiling point of H2O2 is 152. Since there is a difference in boiling points, while heating by 100 degrees, this should evaporate theoretically. But what happens is H2O2 decomposes at 87 degrees. H2O2 decomposes. So, if you start heating this, this is the boiling point. But on heating, it will decompose at 87 itself. At 87 itself, H2 plus O2, you will get at 87 degrees. Means H2O2 decomposes even before it reaches its boiling point. That is the H2O2 decomposes. It decomposes even before it reaches its boiling point. So, how do you find boiling point? That is a different procedure there, that is not much. It decomposes. So, if you start heating H2O2, it decomposes even before it boils. So, what should you do? Separate distillation under reduced pressure. Distillation under reduced pressure. So, the boiling point is 152 or the boiling point of water is 100 at a pressure of 1 atmosphere. Suppose the pressure is less, H2O plus H2O2, the pressure you create is less here, less pressure. What happens? Water boils quickly. Less pressure, less atmospheric pressure. Instead of 1 atmosphere, you take half atmosphere. So, H2O boils quicker than that, and H2O2 doesn't decompose. So, this is called distillation under reduced pressure. So, which substances you employ this? Distillation under reduced pressure is employed to separate substances which decompose even before they reach their boiling point. Regarding the reactions of H2O2, there is a peculiarity in H2O2. This OO bond called peroxy bond, you can say it is almost the second weakest covalent bond, second weakest bond. Why? You have too many lone pairs here, two lone pairs. Because of the lone pairs, the bond breaks easily. So, H2O2 decomposes to give H2O and O, loses oxygen very easily. Whereas OH bond is the strongest bond, second strongest bond. OH bond is very strong, OO bond is very weak. Therefore, H2O2 in all its reactions want to become H2O by losing oxygen. So, what will it do? So, H2O2, because of the weak peroxy bond, so all substances that contain that peroxy bond, they lose oxygen very easily. So, there are host of substances H2O2, O3, CaOCl2, bleaching powder, HClO, NaClO, like that. All peroxy substances. All peroxy substances. H2O2 wants to become H2O. Why? Because H2O is very stable, because OH bond is very, very strong, you can't break that easily. And OO bond is very, very weak, that breaks very easily. O3 wants to become O2, CaOCl2 wants to become CaCl2. The reason, the OCl bond, once again, the same reason, 2 lone pairs, 3 lone pairs. Once again, too much of repulsion. HClO wants to become HClO, same reason. This is HOCl. NaClO wants to become, so ClO, once again, ClO bond is very, very weak. all peroxy substances want to become oxy substances. So these are all less stable due to that extra oxygen. And now that extra oxygen will come in as handy. All these are laboratory reagents. Laboratory reagent means if you want to oxidize somebody, reduce somebody, you can use any one of them. They are all oxidizing agents, reducing agents, because they can simply give an oxygen. They will give an oxygen, and in fact they can even take an oxygen, H2O2, if you want, H2O plus O it can give. If you give an oxygen atom, it will take once again to become H2O and O2, H2O and O2. So extra oxygen and this oxygen O2. So H2O2 is an oxidizing agent, is a reducing agent, gives oxygen, takes oxygens. Not only that, it is an acid also, H2O2, since it has that OH groups, it's a dibasic acid. It is slightly acidic also, weak acid, and it is a bleaching agent, antiseptic. So when you add any one of these two, bacteria, what happens? We all live off oxygen and bacteria dies of oxygen, because bacteria can live only in an environment where there is no oxygen. Its respiration process is called anaerobic respiration. In the absence of oxygen only it can survive. You know why? That's why bacteria lives in places where there is no oxygen, dirty water, etc. Bacteria lives. So when you add them, oxygen is produced and all of them die. So antiseptic, antibacterial, and it is what do you call, water purifier. All these, any one of them can be used to purify water. So chlorination is done to purify water, ozonized drinking water. So bleach, it removes color, because that oxygen once again is responsible for removing color. Colored substances, that when you add H2O2, that color is lost. Now it's very easy to predict the reactions. They are reducing agents, oxidizing agents, and many. For example, Na2SO3 plus H2O2, what will happen? Na2SO3, sodium sulfite. Okay, this sodium is a spectator, Na plus is a spectator, forget about that. Only sulfite is reactive. Sulfite SO3 2 minus, S double bond O, O minus, O minus. It has a lone pair and it is pyramidal. Therefore, non-metals want to form as many bonds as possible. Sulfur prefers to form 6 bonds rather than 4 bonds. Why? To get rid of those lone pairs. To get rid of lone pair, to avoid lone pair bond pair repulsions. So sulfite wants to become sulfate. So H2O2 gives an oxygen and this fellow takes an oxygen. You get Na2SO4 and H2O. So the wishes of both H2O2 and SO3. So what did I say? Non-metals want to form as many bonds as possible. They want to form as many bonds as possible. Now, Na2SO4, H2O. KNO2, H2O2. Same thing once again. KNO3 and H2O. This Li plus, Na plus, K plus, all these are spectators. Nothing will happen to them in any reaction. They remain as they are. Li plus, Na plus, K plus, they are all, we can say they are spectators. And even starting magnesium 2 plus, calcium 2 plus, etc., they are all spectators. So even though it is Na2SO3, for me that is SO3 2 minus only. I see only sulfide, I don't see Na2 there. I don't see K here, it is only NO2 minus for me. NO2 minus, KNO2, H2O2, KNO3 plus H2, like that. You can predict any reactions like this. FeCl2 plus H2O2 plus HCl, say. What happens is, once again this ferrous is a reducing agent, Fe2 plus. We learned what a reducing agent is in periodic table. What is a reducing agent? One who gives electrons. So this Fe2 plus gives electrons because it wants to become ferric. You should know the reason. I've been using the word ferrous wants to become ferric, H2O2 wants to become. You should ask me why they want to become. Means there is some benefit. What is the benefit you observe? Ferrous, the electronic configuration is 3d6, 3d5, half-filled configuration. So since it gets half-filled configuration, ferrous is ready to lose an electron. But who will take the electron? So the oxygen of H2O2, the oxygen of the oxidizing agent, by taking the two protons from acid and 2 electrons, it becomes H2O. This is the underlying principle of all chemical reactions. Oxygen of H2O2, 2 protons and 2 electrons. 2 protons, 2 electrons from reducing. Who gives electrons? Reducing agent. Who gives protons? Acid. That's why I have taken an acid also here. What is the role of HCl here? Nothing. It produces H plus. What will happen? This oxygen, the electrons, the protons put together, they give H2O. Because all oxygen atoms, if possible, they want to become H2O, because H2O is the very stable molecule. OH bond is very, very, very strong. So ferrous is a reducing agent. What happens? Let us see. FeCl2 plus H2O2 plus HCl. It becomes FeCl3. H2O2 becomes H2O. And what happened to that extra oxygen? The additional oxygen, the second oxygen of H2O2. That oxygen, the electrons here and the protons here, it becomes H2O. I call it the assembled H2O. Assembled in the sense, electrons from one place, oxygen from some other place, protons from the third one. I have assembled all of them. Assembled H2O. So, but you need 2 ferrous ions, because each ferrous gives only 1 electron. So 2 FeCl2, 2 FeCl3, 2 HCl, and everything is automatically balanced. 2 protons from here, 2 electrons from here. So you are seeing FeCl2 here, but I am seeing an electron only here. As far as I am concerned, FeCl2 means it is only 1 electron provided. It provides 1 electron. 2 electrons, 2 protons, oxygen. Oxygen comes from 2 electrons from this, oxygen from this, 2 protons from this. All of them assemble and H2O is formed. All these 3, this plus 3. And everything remains. After giving a electron, Fe2 plus becomes Fe3 plus. And of course, it wants 2 chlorines. Okay, 2 chlorines are coming from HCl, 2 HCl. Now, that is how we have to balance redox reactions, by looking at how many oxygens are being converted to H2O. Now, so that way you can predict. So in some reactions, H2O2 can even take oxygens also. What happens? H2O2 by taking an oxygen. So this is precisely what is H2O2, 2 protons plus 2 electrons plus O2. Look here. What happened? The 2 hydrogens are broken. Hydrogen atom, electron and proton, this is hydrogen atom. So when you combine an electron and a proton, what you get is a hydrogen atom. See, this is electron, this is proton. Combine them, electron and proton, nucleus, peripheral. Okay, important is this. This is the nucleus, this is important. This is only a cap, it is only, that's all, hydrogen atom. So these 2 hydrogens are broken, they are into 2 protons and 2 electrons, oxygen. Therefore, what are you getting? What is H2O doing here? Giving electrons. In this reaction, giving electrons, what do you call? Reducing agent. One who gives electrons is called a reducing agent. Reducing agent. Now, means H2O2 supplies those protons, electrons to another person's oxygen. Next, H2O2 can take 2 protons and 2 electrons once again to become H2O plus H2O assembled. The one we have seen earlier. This oxygen, these protons and these electrons assembled, H2O plus H2O. Now, So what is H2O2 doing here? Taking electrons, the opposite. Taking electrons. One who takes electrons is called, gives is called reducing agent, takes is called opposite, oxidizing agent. So here it is giving protons also, therefore acid. So H2O2 is an acid, a reducing agent, an oxidizing agent, a water purifier, an antiseptic, antibacterial, and above all a bleaching agent. Bleaching. Colored substances contain a loosely held oxygen, and this oxygen and that loosely held oxygen of the colored substances, they go away, giving O2. That is called bleaching, removing color. Now, between, this is a previous IIT question, between Na2O and Na2O2, which can turn red litmus white. Red to white, this is a peculiar reaction. We hear red litmus and blue litmus. What is this white litmus? Red litmus to white litmus means removing color. Red to white means bleaching. So, removing color. Who can remove color? Between Na2O and Na2O2. Who can bleach? Bleaching agent means extra oxygen, this peroxide, Na2O2. Weak OO bond, peroxide. So, this will do. This is it. Now, volume strength of H2O2. It is measuring the concentration of H2SO4, H2O2. So, we have molarity, normality, percentage, weight by volume. There are many units of concentration, and this is volume strength again is one more unit of concentration, volume strength of H2O2. Look here, what do you mean by this? 22.4 volume H2O2 solution. Somebody says it is 22.4 volume. A bottle is labeled as 22.4 volume H2O2. There is a label on a bottle. It is 22.4 volume H2O2. What does that mean? That means 22.4 volume H2O2 solution means 1 liter H2O2 solution, 1 liter H2O2 solution on heating 1 liter 22.4, this one, you take 1 liter and you heat it. On heating, it can produce 22.4 liter oxygen at STP. This is the meaning of that. What do you mean by 22.4 volume? You take 1 liter, you heat it, you get 22.4 liter oxygen at STP. So, when I say 10 volume, what does it mean? 1 liter gives 10 liters of oxygen at STP. You may be surprised how to get 22.4 liters from 1 liter. Remember, this is a solution, this is a gas at STP. So, volume of a gas can be anything. So, 1 liter H2O2 solution giving 22.4 liter oxygen at STP. Now, what does that mean? H2O2 solution, you have H2O plus H2O2, right? On heating, what will happen? H2O plus H2O2 on heating. Who will give oxygen? You know H2O won't give oxygen. H2O is very, very stable. It won't give any oxygen. Therefore, it is H2O2 only that is giving oxygen. So, you are getting 22.4 liter oxygen means 1 mole at STP. I mean, this is called 1 mole. 22.4 liter STP means 1 mole. So, you are getting 1 mole oxygen. 22.4 liter at STP means it is 1 mole. 1 mole 32 grams, that is not necessary. The mass of this is not necessary. You are getting 1 mole oxygen means, how can you get 1 mole oxygen? Look at the balanced equation. 2 H2O2 on heating gives 2H2O plus O2 means you get 1 mole from 2 mole H2O2. So, you are getting 1 mole oxygen means that is possible only if you have 2 mole H2O2. 2 mole in 1 liter. 2 mole in 1 liter means molarity is 2. So, instead of saying 2 molar or molarity is equal to 2, another language is 22.4 volume. So, what do you mean by 22.4 volume H2O2 solution? Look here. I will redefine that. 1 liter H2O2 solution which has enough H2O2 to produce 22.4 liter oxygen at STP. This is the meaning of that. Now, so to get 22.4 liter oxygen, if you want to get 22.4 liter oxygen, it's possible only when you have 2 mole, that is 68 grams. But you are getting this 22.4 from 1 liter. So, 1 liter H2O2 solution which has enough H2O2. How much H2O2 it should have? Enough means it should have 2 mole, 68 grams. So if only you have 2 mole H2O2 in 1 liter, that 1 liter can give 22.4 liter oxygen at STP on heating. If only you have 2 mole H2O2, 68 gram H2O2 in 1 liter, then only that 1 liter solution can give 22.4. So, to conclude, 22.4 volume H2O2 solution means 2 molar, 4 normal. Normality will be 4 because molarity is equal to 2. Since H2O2 is a dibasic acid, its normality is 4. The N factor of H2O2 is 2, means H2O2 can take 2 electrons, can give 2 electrons, can give 2 protons. Any ability of H2O2 is 2. Therefore, it is equal to 2. Its ability is 2. Therefore, 1 mole is equal to 2 equivalents. So, 4 normal and 6.8% volume by volume. This is it. 22.4 volume H2O2 solution means 2 molar, 4 normal, 6.8% weight by volume means 68 grams in 1 liter, 6.8 grams in 100 ml, 6.8 grams in 100 ml, 6.8% weight by volume. Now, let us do a few problems. Volume of H2O2 solution, volume strength, volume of oxygen at STP, produced at STP, molarity, normality, percentage weight by volume. Look here. So, you are hearing volume, volume, volume. Don't be confused. This is volume of the solution, volume present in a bottle, volume present in a bottle, volume of the bottle, volume of H2O2 solution. Volume strength is the label you put on it, the concentration. I mean, molarity, normality, volume strength, these are concentrations. And volume of oxygen, this is the volume of the gas. So, this is about the solution, this is about the gas, this is concentration. But in all of them, you have volume, volume, volume. Don't be confused. Volume of the solution, volume of the gas liberated, and volume strength, which is actually the concentration. Now, I am taking 10 liter, (112 liter). Now, find all the others. These two I have given. What is the question? 10 liter H2O2 solution on heating produced 112 liter oxygen at STP. 10 liter H2O2 solution on heating produced 112 liter oxygen at STP. So, 10 liter, 112 liter. Find remaining. So, what is volume strength? 1 liter, how much? So, if you take 10 liters, you are getting 112. If you take 1 liter, you get 11.2. This is called 11.2 volume. Volume strength is 11.2. According to definition, whatever you get on heating 1 liter, it is called volume strength. 10 liters, you get 112 liters, 1 liter 11.2. So, when it is 22.4 volume, the molarity is 2, 11.2, molarity 1. When molarity is 1, normality will be 2. 6.8, when this is 2, this is 6.8, when this is 1, this is 3.4. Bas. Just definition, using the definition. So, 112 liter oxygen means, 112 liter oxygen means it is 5 mole oxygen. To get 5 mole oxygen, you need to have 10 mole H2O2. 5 mole oxygen, you need to have 10 mole H2O2. 10 mole in 10 liter, 1 mole in 1 liter, molarity 1. So, makes sense once again. This is what is given, 112 liters. 112 liters means 112 by 22.4. This is 5 moles, 5 mole oxygen. To get 5 mole oxygen, you need to have 10 mole H2O2. 5, 10. 10 mole in 10 liters. So, 1 mole in 1 liter, that is molarity, number of moles in 1 liter, 1 mole in 1 mole per liter. 2 equivalents per liter, 1 mole is 2 equivalents. 1 mole is 2 equivalents, 2 equivalents per liter, and of course 1 mole means 34 grams. 34 grams in 1 liter, 3.4 grams in 100 ml. 2. Hundred liters, 10 volume. How much oxygen I will get? 10 volume means 1 mole gives 1 liter gives 10 liters. 1 liter gives 10 liter. 100 liters gives 1000 liters oxygen. 1000 liters. 10 volume. 22.4 means 2 molar. 10 means how much? You write the proportionally. It will be okay. 22.4 is 2 molar. 22.4 volume is 2 molar. 10 means 10 by 22.4, roughly how much ever that will be, you just calculate. Okay, you find out the relation. Just using 22.4 is equal to 2, 10 is equal to how much? 10 becomes how much? Now, like that, volume strength of H2O2. So, that's all about H2O2. Hard water, H2O2 we have studied. Now, heavy water. Heavy water. D2O. There is not much to study about heavy water. I will just briefly explain heavy water. D2O. Why is this called heavy water? Because you have 3 isotopes of hydrogen, H11, H12, H13. What are isotopes? Same atomic number but differing mass number, because protons and electrons will be fixed. Neutrons can be anything. You can have, here you have 1 proton and 0 neutrons. There is no neutron at all. Here you have 1 proton and 1 neutron. Here you have 1 proton and 2 neutrons. This is called protium. H11 is called protium. H12 is called deuterium. Deuterium. H. This is called tritium. HDT. So, only the isotopes have different names. Different isotopes have of hydrogen only have different names. You can't expect everywhere every isotope to have a separate name. Protium, deuterium, tritium. So, it is heavy because it has one more neutron. So, the water that is made of deuterium and this tritium, because it has too many neutrons, it is radioactive. It is radioactive and beta decay. Radioactive, it decays beta particles because it has too many neutrons. One of the neutron is converted to a proton and electron is sent out, beta decay, beta minus decay. Now, so heavy water D2O. Manufacture of heavy water, it is manufactured by electrolysis of N by 2 NaOH solution. N by 2 NaOH solution. Look here, where is D2O present? You don't have separate water bodies for D2O. D2O is present in all water bodies. You have D2O in rivers, you have D2O in seas, tanks, water tanks, everywhere. You have D2O wherever H2O is present. But the thing is, 6000 milliliters of water, 6000 ml H2O contains 1 ml D2O. So, that is the ratio. 6 liters, in 6 liters you just have a drop, one drop. So, when you electrolyze N by 2 NaOH, what happens? Water gets out first and heavy water remains, N by 2 NaOH solution. Electrolysis of N by 2 NaOH solution. And when it comes to properties, look here, physical properties. Charge related properties, more for water, more for H2. Mass related properties, more for D2. Let me explain what I mean by this. What are charge related properties? Dipole moment. You know, dipole moment is because of H plus O minus, dipole moment. And ionic product, the concentration of ions, H plus ions, OH minus ions, Kw. And dielectric constant, the charge separation between capacitors. Dielectric constant, more for H2O. And salts are more soluble in H2O. Solubility is once again charge related, polar. So, polarity and what else? Solubility of salts, solubility of substances, solubility of salts. All these are more for H2O. And what are mass related properties? Mass related means something like van der Waals. Boiling point is more for D2O. Of course, density, viscosity, surface tension, all these mass related where cohesive forces are also involved, since it has an additional mass of 2 units. So, all these are more for D2O. And temperature of maximum density, water has a maximum density at 4 degrees, whereas H2O has a maximum density at 11.2 degrees. The density is maximum at 11.2. So, all these charge related properties more for H2O, mass related properties, you have to learn broadly, otherwise you can't remember each and everything very simple. Charge related, dipole moment, polarity, dielectric constant. Now, what about chemical properties? Chemical properties, same for both H2O and D2O. Same. I will tell you what. For example, reactivity with water, or sometimes it is called hydrolysis also. Suppose you have aluminum nitride. Hydrolysis means you break the bond. Hydrolysis means break the bond. Which bond? Break the bond between two atoms. Break the bond between two atoms. H plus on one side, OH minus goes to another side. Where will H plus go? Whoever is more electronegative. Who is more electronegative? We already know. FONCl, that is the order of electronegativity. FONCl greater than H greater than B, like that. And OH minus goes to whoever is more electropositive or whoever is more metallic. So, aluminium plus nitrogen minus. So, H plus goes there, OH minus goes there. How many? Depending on their valency, they are plus 3, minus 3. Here aluminum is plus 3, this is minus 3. Therefore, you give 3 hydrogens here, 3 OH here. What will be the product? AlOH thrice, aluminum hydroxide plus NH3. So, aluminum nitride reacts with water producing aluminum hydroxide and ammonia. So, same aluminum nitride reacts with D2O producing 3 OD and 3 D. Same, and you get Al OD thrice and ND3. There is no difference between H and D except for mass. I am telling you, only the isotopes of hydrogen have been given separate symbols HDT. So, this is deuteroxide, hydroxide, deuteroxide, ammonia, deuteroammonia. Put deutero wherever deutero. So, this is called hydrolysis. You call this deuterolysis. Deuterolysis. Since it is done by deuterium peroxide, deuterium oxide, deuterolysis. So, deuteroammonia. This is deuteroammonia. So, before you add D2O, you just do it easily with H2O and copy that to DOD. Then you know the chemical reactions of D2O. Let us look at 2-3 more. Calcium carbide. Calcium carbide. Hydrolysis reacts with water. So, I want actually the reaction with D2O, but I am first reacting with H2O. 2OH, 2H. So, it is 2OD, 2D. So, you get CaOH twice, calcium hydroxide, calcium hydroxide, C2H2, acetylene. Common name is acetylene. CaOD twice plus C2D2, C2D2. This is hydrolysis, this is deuterolysis. You get a deuteroacetylene, deuteroacetylene. There is the matter. Aluminium carbide, Al4C3, aluminium carbide. Break the bond. 12OH, 12H. Why am I using 12OH? Because each aluminium wants 3 OH. 4 aluminum is 4 into 3, 12. Each carbon needs 4 hydrogens, 3, then 12H, 3 into 4. So, you get, what is it you get? So, it is 12 OD and 12 D. AlOH thrice. So, not only reaction with heavy water, you are learning reaction with water also. AlOH thrice plus 3CH4, AlOD thrice plus 3CD4. This is methane, this is deuteromethane, aluminum deuteroxide, deuteromethane. So, you apply a little more, so it's every time I can't write DD, so I'll simply write some reactions with water. Since any case we have learnt, we have to learn the reactions of water. BCl3, break the bond, 3H, 3OH. What will you get? BOH thrice, 3HCl. H3BO3, boric acid, H3BO3, BCl3. SiCl4, break the bond, 4H, 4OH. You get SiOH 4 times, which is H4SiO4. What is that? H4SiO4 are those silicic acid, boric acid, silicic acid. Just like that. BCl3, SiCl4, and you can have any number like this. PCl3, break the bond, 3H, 3OH. Why am I using 3? You should know I am breaking 3 bonds. POH thrice. POH thrice. 3H here. H3PO3. H3PO3. In some cases like PCl5, you will be getting 5OH. 5OH, and some molecules, some atoms cannot have too many OH groups. So let us generalize maximum number of OH groups that are permissible. Maximum number of OH. Silicon can handle 4 OH. Phosphorus and boron can handle a maximum of 3. Sulfur only 2. Chlorine, bromine, iodine, nitrogen, carbon, etc. they can handle only 1 OH group, maximum number of OH. The reason, since OH groups are strongly electron withdrawing, the central atom becomes too positive, and as the electropositivity increases, the tolerance towards OH groups is increasing. Chlorine only 1 OH, sulfur more positive, okay, 2 OH, phosphorus a little more positive, 3 OH, silicon more positive, 4 OH they can handle. So PCl5, when you break normally 5H, 5 OH. You are getting POH 5 times. POH 5 times. Nothing wrong in calling it as H5PO5. There is nothing wrong at all. H5PO5 is perfectly all right. But it is H3PO4 dot H2O. H3PO4 dot H2O, hydrated phosphoric acid. Maximum number of OH groups that can be permitted. So, out of interest, let us hydrolyze CHCl3. CHCl3. What do you mean by hydrolysis? Break the bond. 3H, 3OH. Why I am breaking 3 bonds only? CH bond cannot be broken, remember, because there is not much of a polarity. Plus minus, there should be some polarity. Chlorine minus plus. So break the bond. H there, OH here. So CHCl3. What is it you are getting? HCOH, OH, OH. Water, H2O. So carbon cannot handle 3 OH groups. Carbon can handle only 1 OH. So you have HC double bond O, OH, HCOH, formic acid. Chloroform on hydrolysis gives formic acid. B2H6. Hydrolyze that carefully. B2H6. Break the bond. H plus on one side, OH minus on the other. Where will H plus go? H plus, I said, will go to whoever is more electronegative. And what do you remember about electronegative order? FONCl, hydrogen greater than boron. Hydrogen is more electronegative than boron. Hydrogen. That's why even in this 2 electron 3 centered bond, hydrogen was able to attract the electrons towards itself and then transfer them to boron. Hydrogen is attracting electrons towards itself and then transferring the electrons to boron, and like this 2 electron 3 centered bond. These 2 electrons come to hydrogen and they go here and come back. 2 electron 3 centered bond. Now, so hydrogen is more electronegative than boron. So 6H, 6OH. H minus, this is minus, this is plus. So always you have to see those invisible plus minus. Means you need not write plus minus, but you should feel that boron is positive, hydrogen is negative. So what happens? BOH thrice. BOH thrice. 2 BOH thrice, and of course something like that. Boric acid. B2H6 once again use boric acid and hydrogen. Carefully. NCl3. NCl3. Break the bond. Who is plus, who is minus? Nitrogen more electron than chlorine. FONCl. Chlorine is next to nitrogen. Therefore, H here, 3H3OH. You get NH3, 3HOCl. So in P block, you will see so many reactions, so many compounds reacting with water. There we won't learn hydrolysis separately. I have taught hydrolysis here. Hydrolysis, my definition of hydrolysis is reaction with water. Reactivity with water. Now, NCl3 use ammonia. Calcium cyanamide CaNCN. Where to break the bond? Wherever there is electronegative difference. Break the bond here, here, here. 2OH, 3H. Any number of H and OH can be used. There is no rule because H and OH are plentifully available in water. 3H, 4OH, 3H. So what is it you got? Calcium hydroxide, ammonia, COH 4 times, H2O, because carbon cannot handle more than one OH. Automatic loss of water. Water is lost automatically. You get COH 4 times is nothing but carbon dioxide. So this calcium hydroxide and carbon dioxide end up giving CaCO3. So what is the net product? Calcium cyanamide CaNCN or CaCN2 plus H2O. How many H2Os are involved? So many are involved, finally 2 are released. So here 6 H2Os are involved, 2 hydrogens, so 4 H2O. Effectively 4 H2Os are used. You get calcium hydroxide and carbon dioxide. You get calcium carbonate, one more H2O here. Therefore, effectively only 3 H2O are used because it is forming CaOH twice and then losing H2O. So 6 waters are involved here. 6 H, 6 OH we have used here. 2 water are removed here. 1 water is removed here. So 3 HO, CaCO3, 3 and then 2 ammonia, 2 NH3. This is manufacture of ammonia by cyanamide process. Calcium cyanamide and hydrolysis reacting with water gives ammonia. CH3CN, cyanide, hydrolysis, break the bond. 3H, 3OH, CH3COH. Remove water. Why am I removing water time and again? Carbon cannot handle more than one OH. One OH, remove water. You get CaCH3COOH, acetic acid. So cyanides give carboxylic acids. Cyanides on hydrolysis give carboxylic acids. So across chemistry, all chapters, be it organic, inorganic, you need to learn reaction with water. And warning, the symbols for hydrolysis. No one will tell you that this is a hydrolysis reaction. Symbols of hydrolysis, you find H3O plus, H2O H plus, H2O OH minus, dilute acid sometimes. All these symbolize hydrolysis. H3O plus means hydrolysis. H2O H plus, dilute acid, aqueous base, dilute acid, aqueous base, and all these are symbols for hydrolysis. And no hydrolysis for these carbon-carbon bond. Don't try to break carbon-carbon bond because it's not polar. Carbon-carbon bond, carbon-hydrogen bond, any bond involving fluorine, except with xenon and boron, means NF3, no hydrolysis. Nitrogen fluorine, no hydrolysis. Xenon fluorine and hydrolysis of xenon fluorides we have to learn separately. Now, CCl4 doesn't undergo hydrolysis. CCl4, a net non-polar molecule, doesn't undergo hydrolysis because of non-availability of vacant orbitals, some reason. Carbon, hydrogen, CCl4, any bond involving fluorine except with xenon and boron, like that. Salts of strong acid, strong bases. Salts of strong acid, strong bases, they don't undergo hydrolysis. This is a different hydrolysis, salt hydrolysis, but no hydrolysis for strong acids, salts of strong acid, strong bases. C double bond O, don't try to break C double bond O because you will get once again get the same. Even if you break C double bond O, you will get C double bond O only. That is all about hydrogen and its compounds.